What is physical geography? Before we actually talk about physical geography, I want to take a look at a couple universal geographic concepts. But before we even look at those concepts, I wanted to share with you this picture that I have down here. And this is not twins. This is a friend of mine. And we took the iPhone and we did the panoramic photo. So I took one picture, then she ran behind me and then was at the other side of the cave. And then I finished up with the panoramic shot. So we were able to get her on two sides of the picture. But that's not the point of the picture. The point of the picture is the cool image that you're looking at, this cave and this black sand. This is a black sand beach, and you're looking at a lava cave. And if you look really closely, you'll notice that the cave has lava tubes essentially that are oxygons or octagons. They all have multiple sides associated with them. And if you take a really close look, it looks like this lava has sort of flowed and it's cooled in ribbons. And that's exactly what happened. And so you take a look at this picture and it becomes a head scratcher. And you go, where was this picture taken? What is this? And how did this happen? Well, this is in Iceland, and this is one of the black sand beaches in Iceland. And the black sand is all due to the erosion of lava flow. And you're looking at this lava cave. And the reason why you get this lava cave was due to how quickly the lava actually cooled when it was flowing out of a volcano. So it's pretty interesting stuff. Now, Iceland is more than just looking at cool lava and cool landscape. There's a whole cultural phenomena associated with Iceland in terms of history. If we talk about something, for example, like the French Revolution and what started the French Revolution, the French Revolution we know was really spurred on by famine and people getting hungry, not able to make a living. It just wasn't working out well. And the question is, what instigated that famine? Well, history has actually shown that there's a very large volcano in Iceland. And predating the famine in Europe, you had this volcano erupt. It sent up so much ash into the atmosphere, it went across Europe, covered Europe, blocked out the sun, and essentially created a multi-year famine. That famine led to unrest, it led to animals dying, led to people starving, and it really led to the French Revolution. This is now a historical fact. So when we take a look at physical geography, it's not just the landscape we look at, and it's not just the physical forces that help shape the landscape, but rather it's going to be what is the influence to that landscape on humanity and vice versa. Because the anthropogenic influences to what we're seeing cannot go unnoticed. And so when you take a look at things like climate change and you talk about climate change and you ask, well, where is climate change actually coming from? Well, we're going to take a look at physical geography because one can't go without the other. So when we take a look at geographic concepts, those are really important to what we want to talk about in terms of physical geography. So how do we think geographically? How do we think spatially? Very important questions in physical geography. How do we use mental maps to highlight the importance of asking geographic questions? Mental maps we'll get into in just a second, but that is our shared or individual understanding of a certain place. And so mental maps is going to form a lot of our. So what is a mental map? So again, mental map is what you know and how well you know it. Maps of the environment stored in our brains that reflect the amount and the extent of geographic knowledge and spatial awareness that we possess or lack thereof. Mental maps, though, I'll go even a step further. It's not just how well you know a place, it's sort of how well you know something. We're living right now in a political environment that's been building and brewing for the last decade. And now we're watching TV and we're seeing various political rallies. And I'm sure if you're like me, you're watching TV, you're watching a political rally, and you're scratching your head going, what in the world are these people thinking? How in the world can they support this particular candidate and what they are saying seems to be so far off. How is this possible? And the answer sort of becomes mental maps. People know what they know, and sometimes it's a hard shell to break to try to bring other content or concepts into your mental capability. And so, what I always tell students is your mental map is what it is now. And our goal is to expand that mental map so that you can be more of a thrifty student. You can be more of a critical thinker. You're not going to be locked into a particular narrow thought process, but if you can become open and add more content to your mental map capability, then you're going to be much more aware of the world that's around you, become a better student, and frankly, become a better steward. So here's a nice little example I like to use. If you travel a lot, and let's say you go overseas and you say to somebody who you're talking to, hey, I'm from Southern California, and they might say, oh, Los Angeles? And you say, yes, Los Angeles. So what are they going to tell you? They're going to tell you, okay, I know something about the Pacific Ocean. Maybe they've heard about Santa Monica or Hollywood, so they know about the Hollywood sign, right? And even if you're watching the Paris Olympics and they handed the torch off to LA, I mean, who did you see? You saw Snoop Dogg, you saw the Red Hot Chili Peppers, you saw Santa Monica, beaches, the Hollywood sign, right? That's what they showed because that's what people know of Los Angeles. Now, if you know a little bit more, maybe you know that there's UCLA out there and there's LAX out there, and maybe there's some mountains out there. So you understand a little bit more if maybe you visited once or twice. Now, for me, if you ask my kids something about Los Angeles, they will say Staples Center, not so much crypto, Staples Center. They'll say the Ritz-Carlton next to Staples Center. They'll say UCLA, and they'll say traffic. Now, how do they know all these things? They know all these things because when my boys were younger, we were a huge Laker family. And so my boys loved the Lakers. I mean, as a matter of fact, both the kids shed a tear when Kobe Bryant died. I mean, this is serious stuff in our house. We couldn't afford to take our kids to Laker games every year because it's too expensive. But what we did do was we made them a promise and said, we will go to a Laker game every year, but that includes preseason because you can get preseason tickets for real cheap. So every year we would go to a Laker game. And we kept that tradition alive when my oldest boy was 6, all the way till he was 18. We were going to Laker games, one of them annually. Most of them were going to be preseason games. So that's what my kids know about LA. Staples Center, they know exactly where it's located. They know exactly where UCLA is located. And they know exactly where UCLA is located because they were both applying to go to UCLA as well when they got a little bit older. So again, their mental map has expanded based upon their desires, and their desires have led them to what they know. And so I think the key to expanding mental maps is to learning more about your wants and needs, but just have a pure expansion of thought. And so, again, when we take a look at mental maps, when we look at all these things, all these mental maps here, we know that north is up. That seems to be sort of a common practice that most people think that north is up. So, okay, cool. All but the first map identifies some prominent feature and landmark. Great. But what's not common is one map highlights Staples Center, Dodger Stadium, and the Coliseum. So again, the expanse of knowledge comes with teaching and with experience and with generally just simply wanting to know. Now, what you include and omit on your map, on your personal map, by choice or not, is going to speak volumes of your geographical knowledge and spatial awareness. But the beauty is we can all increase our knowledge and awareness. And so part of our task in this particular class is trying to do just that. I'm sure all of you have some semblance of understanding of Southern California, for example. You know what our weather is like in San Diego, and you can tell somebody what our weather is like in fall, spring, summer, and winter. You also know something about our vegetation. You know that we've got low-lying shrubs, chaparral. You know that it varies in various places. You know Torrey Pines is a certain way compared to even San Marcos, which is different than Chula Vista, but there's similarities and there's differences. You know that from your experiences. But have you ever asked the question, why is there Torrey Pines at Torrey Pines? Why is there shrubbery here called chaparral in Southern California? Why is it that if I showed you a picture of San Diego and Tuscany in Italy, that they would look very similar? Why is it that kelp in the ocean here is red? Why is there a plant that has a small leaf versus a big fatty leaf? So all of those questions are ones that we want to address. That's the goal of this class, is increasing your common knowledge and adding content to it. And in this case, we're concentrating on physical geography because that's what we're here for, physical geography. Okay, so those are mental maps. And there are 6 major themes when we talk about geography in general. And we're going to ask these geographic questions as well as we proceed through the class. So number 1, geography is all about location. Location answers the questions of where. Keep that in mind. Location answers the question of where. Where is what and why is it there? Region is the portion of the Earth's surface with uniform characteristics. How do they change? How do they interact? And again, we can talk about San Diego as a region, but then I can also talk about San Diego as being a particular type of climate region. And this climate region here could be very similar to a climate region halfway around the world. And the question is, why is that true? We also want to take a look at human and Earth relationship. This is perhaps one of the most important things. How do humans affect the environment? And we really want to latch onto this. I've always scratched my head to a certain extent about how certain things can become political wedge issues. We all live on the Earth. Climate is a big deal. Farming is a big deal. How climate affects farming is a big deal. And it shouldn't be one group saying you're lying and fabricating stuff. That doesn't make any sense. We can all agree that the economy and the environment becomes a balancing act. And how can you support the economic conditions of people and still be good stewards to Earth, knowing that it affects us and it affects the future of our societies? That really ought to be the only question, but instead, human-Earth relationships have become political wedge issues. So what I always try to impress upon students is, don't make it a wedge issue, just learn the facts. Know that you're smart about these facts, and then you can share that information with your friends and family. That's really the best thing that we can do. Place is also another theme in geography. The characteristics that make each place unique or similar for that matter. We talk about movement, diffusion across Earth's surface, but it's not just the movement of people. It's the movement of rivers, the movement of air, weather dynamics. The question becomes, why is one place drought-ridden, whereas the other place is a rainforest? What's that? That's the diffusion of energy now across the surface. So movement is a big deal when we talk about geography. And then finally, relationships. Relationships between natural systems, geographic areas, society, cultural activities, and the interdependence of all these variables over space and time. That's the biggest element of geography. Now, to me, these are all cool. Like, this is really cool stuff. And again, keep in mind that I got a degree in physics from the University of California at Santa Barbara. Graduated UCSB, and I went to San Diego State University, and I got a degree in astronomy. And I was set. I was ready to go. But then I went to the University of Arizona in Tucson to study planetary science. And I was there in the very first class, and we spent multiple weeks talking about craters on the moon and how you can count those craters. Now, for a lot of people, that's going to be fascinating stuff. But for me, it wasn't. And I was thinking back to my days as an astronomy student at San Diego State, and my most enjoyable classes included remote sensing, trying to figure out the features on our planet from afar, and then meteorology, the discussion of weather and climate. I loved those. And I hearkened back to when I took those classes and where I took them. And I took them whilst I was an astronomy student, but those were classes being offered in the geography department. So I came back to San Diego and I signed up to be a master's student in geography. And that was principally because of relationships. That to me was everything. That to me was science, which a cultural collaboration, which to me made it worthwhile and of value. And so geography is very personal because, again, what we study, whether it's cultural geography, physical geography, political geography, it doesn't matter. The human earth relationship, that's what builds it. And that's what makes it, to me, a particularly interesting physical science. So that's physical geography, sort of. Those are the elements of geography and geographic thought. But what's the nature of science? Because this is a physical science class, and you all are here fulfilling that general education in physical science. Well, we know science unto itself is a body of knowledge. It's a method for understanding, organizing, and communicating knowledge. That's what science really is. Scientific discovery and advancement always begins with curiosity, and we essentially observe a phenomena and ask questions. Observing a phenomena and asking questions. It's not observing a phenomena and making a statement and then that's it. It's observing a phenomena and asking questions, trying to come up with a statement that says that's it. So the nature of science really becomes the use of the scientific method. And like all other sciences, geography uses the scientific method to help solve problems. It really is just a logical way to think. Okay, so what are the elements of the scientific method? And what are we going to be looking at in this class? Well, you observe something and then you ask a question. So let me give you an example. Let's say I observe a plant and this plant looks strange without a better adjective to use. It looks strange, it looks funny, and the question is, why does that plant look the way it does? And let's say, for example, I was talking about something like, let me ask you. Okay, I've got somebody's feedback going on right now. So can I just have everybody mute? Perfect, thank you. So let's say you see a plant, maybe it's me. Let's say that you see a plant and there's this plant called a welwitschia. And the welwitschia is a fascinating plant. As you probably know, plants do photosynthesis. Plants will take solar energy, convert it into a chemical form. This chemical form now enables the plant to grow and to survive and thrive, and then other animals can eat the plant and ingest this chemical energy. And so now the energy, which is started from the sun, moves to the plant, which moves to the animals. But what if I observe the welwitschia doing photosynthesis at night and not during the day? That almost doesn't make any sense. How can a photosynthetic plant do photosynthesis at night and not during the day? So I'm going to ask a question. I'm going to say, why is this happening? How is this happening? Right, those are my questions. And now I need to develop a hypothesis. So maybe in terms of welwitschia, well, I look at where it grows. Welwitschia is pretty much a desert dwelling plant. And so my hypothesis is going to be, well, maybe it's so hot and dry at this particular location, maybe it's more efficient for the plant to do photosynthesis at night because there's going to be more moisture available. But that's only part of my hypotheses. The next part has to be, well, if that's the case, how does the plant actually do this photosynthesis at night? So I'm going to come up with something. Then I'm going to test my hypotheses with experiment or experiments. I'm then going to take a look at the data. I'm going to draw conclusions. And if my hypothesis is not supported, I'm going to go back to start and develop a new hypothesis. If my hypothesis is supported, I might test the hypotheses with even further experimentation and continue revising my hypotheses and experimenting even further. If I continue along and my hypothesis is continually supported, I now have the foundation to develop a theory. That is the scientific method. You don't go from the top to the bottom and skip the middle. You can't do that. So science is robust, it's rigorous, it's difficult to come up with conclusion because you definitely have to go through series of steps in order to get to your theory. And once you develop a theory, that's not the end of the game because you're still going to have people continually asking questions, continually developing hypotheses, and continually judging. Always and forever, that is the scientific method. So it's an extremely rigorous but very logical system, and it's sort of a good way to look at stuff. Like if you want questions, develop hypotheses, test it out. Now, the types of data often used when we're talking about scientific method is qualitative data or quantitative data. So qualitative data can be as simple as color, shape, texture, size. All of that are qualities to which we can collect data and ask questions about. Quantitative data is stuff that can be measured, typically dealing with numbers, length, height, area, etc. So quantitative is quantity. So when we're looking at the scientific method and when we're looking at various types of data, we can look at all going to go together in our quest to solve problems, looking at the data. Now, here's the caveat. That's the scientific method for all of science. In geography, though, we always have to think spatially because geo is geography. We got to think spatially with this stuff. So step one, we ask a question about spatial relationships in the world around you. Step two, you got to acquire data and information you need to answer your question. But again, it's usually going to be spatial data. Step three, you're exploring. You're turning that data into maps or tables or graphs. And you're literally looking for patterns and relationships, spatial patterns, spatial relationships, to see if there's a connection between location and what you are observing. Step four, you're analyzing the data. You're analyzing those patterns and you're analyzing the relationships with respect to your question. So, and we'll use vegetation again as an example. San Diego is down here on the west coast of North America. And then if you go all the way to Tuscany, Italy, it's off the Mediterranean. How is it that those locations, being so far away spatially speaking, can be so similar climately speaking and vegetation speaking? Those are questions we ask that have a spatial context associated with them. And then finally, step five is acting. You use the results of your work to educate, to make a decision, to solve a problem. That becomes the scientific additive when we're talking about geography. Okay, so that is foundational content. Everybody needs to know. You need to know about the scientific method. You need to know about spatial analysis, what the major themes of geography is. And now the question becomes, What's physical geography? I mean, that's why you're all here. That's the punchline. What is physical geography? So let's look at that. Physical geography itself is really going to be the study of the physical forces that help shape the environment. And when we take a look at Earth, Earth is a huge system composed of a series of subsystems that interact and influence one another. So we can start, for example, with the hydrosphere. And the hydrosphere has everything to do with water, H2O. But it's not just the water and rivers and streams and ice. It's going to be water also in the atmosphere. And the atmosphere here is everything to do with air. So what's in the air? I love this photo right here. This is taken from the space shuttle, and this is just the edge of the atmosphere on Earth. And you can see how relatively thin it is versus the thickness or the radius of the planet itself. The radius of planet Earth is like 8,000 miles, and the whole thickness of the atmosphere is like 100 to 200 miles. It's nothing. But without this atmosphere, we wouldn't have a biosphere, which has everything to do with life. So the crazy thing is the hydrosphere, the biosphere, the atmosphere, we all know that they interact and influence one another. And then, of course, there's the lithosphere, which has everything to do with rocks and solid earth and volcanoes and earthquakes. I already mentioned Iceland and how Iceland potentially influenced the atmosphere, which potentially influenced the biosphere, in part because the hydrosphere was influenced by that volcanic eruption as well. And so with geography, it becomes somewhat challenging. You can't think of stuff in a vacuum. Everything is connected to everything. And here's a very quick fun fact for you. Let's say that we take a look at the composition of the atmosphere. The atmosphere is about 78% nitrogen, maybe about 21% oxygen, and then about 1% argon. So argon is a noble, oh, not Ag, that's gold. My pen's not working too well. Argon. So about 1% of the atmosphere is argon. Okay, nitrogen and oxygen sort of make sense. We breathe oxygen. Nitrogen actually makes sense because nitrogen is used by bacteria to grow plants and stuff like that. But this argon, like 1% argon, where did this thing come from? Well, as it turns out, in the lithosphere, there are rocks. And in this rock, there is potassium. Okay, so over time, potassium decays. And when it decays, it eventually decays into argon, a noble gas. So the atmosphere has directly been affected, not just by volcanoes and stuff like that, but by elements that are actually found within rocks, like potassium turning to argon. So again, the influence is everywhere. It is a constant dynamic system. That's why we can't think in a vacuum or in a bubble. The fact of the matter is, what we do to the atmosphere today, if we talk about something like climate change, absolutely affects the biosphere, absolutely affects the hydrosphere. Everything is affected because of this interrelationship of all things on our planet. Anybody have any questions at all? It's fairly foundational and fundamental, but again, if you do, please just let me know. All right, so when we're studying physical geography, it's pretty complex. And in our studies, we're going to make models, physical models, 3D. We'll look at photos. We'll look at mathematical and statistical models. We'll do simulations. We'll do predictive analysis. You might ask me, how do we know as much as you say we do about climate change? A lot of that's going to have to do with formulaic simulations, and I'll talk about that in a little bit. Conceptual models, seeing models, mental maps becomes a big tool in our physical geography understanding. And as I mentioned, today, AI is becoming an absolutely huge resource in how we study complex systems. It really is quite impressive. Now, all these metals and everything, models and everything that we do are used in what's called systems theory. And in systems theory, our quest is to understand how things work and influence each other. And this is like, this is the greatest question of all humankind. This, if everybody had the answer to this, it would make everybody marriages happier and there would be no war. The quest to understand how things work and influence each other. We won't look at it as a social experiment. We're going to look at this, though, as a physical geography experiment or thought process. So, a system itself is going to contain both matter and energy. Let's take a look at something called the hydrologic cycle. So in the hydrologic cycle, we might have the sun in the picture. So we have our solar energy, and our solar energy is emanating from the sun. It goes to the Earth's atmosphere in the form of what's called insolation or incoming solar radiation. We're going to go into more detail than this later. Let's say that we've got some water here, and this will be our H2OL because it's in a liquid format. So, or a liquid form. So solar energy comes down and the surface of the water is heated up. Well, heated water molecule is going to evaporate and turn into water vapor. Now, keep in mind, what is water? Well, water is H2O. It's two hydrogen atoms bound to a single oxygen atom. And the angle between the two H's is really going to dictate what this molecule is. This is water. But if I wanted to have H2O gas, it would actually look like this, where the angle between the two H's is even further. So what happens is energy is going to get absorbed in the H2O molecule. The energy is going to excite and expand the molecule, and that's going to create the evaporation because now we've expanded H2O. We've turned it in from a liquid into a gas. Now this gas, again, is less dense than the liquid, so the gas is going to rise up into the sky. And now we've got our H2O G for gas. But the pressures and temperatures on planet Earth are actually conducive for condensation and evaporation. It's a really quick system. So here, the energy's been absorbed, but almost as quickly, the energy will be released from the H2O gas molecule. And that means that this gas is going to condense and turn back into H2O liquid. And if I get a bunch of H2O liquid, and they're all small water droplets, and they're all suspended in the atmosphere, that's going to make a cloud. So this is the part of the hydrologic cycle. We're taking water from the surface, we're putting energy into it, it's going to evaporate, it's going to rise into the sky, energy will be lost again back into the atmosphere. So now we're moving energy, we're moving this energy, and now we're condensing our vapor back into a liquid form. You can't see water vapor, so when you look at a cloud, you're looking at the water droplets. And that's what we have here. Now, let's say that this cloud now blows over maybe a landscape. And let's say that over the landscape, it rains. So it precipitates, it rains, and this water maybe flows from a river back into the sea. We've now moved matter. So in this hydrologic cycle, we've moved both matter and we've moved energy. This is our system. Here's a quick little fun fact as well. We know that the world is covered by a tremendous amount of water. About 70+% of our world is covered by water. Of that, about 90-something% of it is ocean. So the majority of our water is in the ocean. And there's a lot of water out there. And it's deep. If you go to the Mariana Trench up the Philippines, that's 7 miles deep. That's a lot of water. But because the pressures and temperatures on our planet are conducive for evaporation and condensation, every single water molecule has been through this system multiple times. No joke. Every single water molecule on this planet has been through this system multiple times. The water molecules that are in your body right now have at one point in time been in the ocean, been in the atmosphere, been in a river, maybe even an ice cap, back into the ocean, your body. It's all been through the system. So we look at the world that we live in and we look at it as series of systems and subsystems. And the key to our systems and subsystems is matter and energy. That's the key. That's what we're looking at. Now, when we talk about open versus closed systems, the hydrologic cycle is an open system because neither energy nor matter are confined to the system. They can all move. Most systems on Earth are open: streams, volcanoes, rock slides. In a closed system, energy can cross through the system, but matter itself cannot. So in a closed system, energy can cross through it, but matter cannot. Earth, by itself, as a singular entity, is a closed system because the matter itself is confined to the system, but solar radiation can come in and energy itself can escape. So energy in, energy out, but matter itself is confined to the Earth itself. Now, by the way, if we didn't have this, we wouldn't be here. We would be like Venus. So it's important for the energy to come in and to go out. And that's what we see in the Earth closed system. But by and large, all the subsystems on the planet are considered open because energy and matter are not confined and they can move around the entire planet. Okay. So whenever we talk about systems and when we ever talk about Earth itself, we always have to look at feedback mechanisms because in physical geography, the Earth has a quest for stability or equilibrium. And so the ways to maintain stability is via positive feedback, negative feedback. And I really want to make sure that we understand that negative and positive does not mean good or bad. Negative simply means that there's a resistance to change to stabilize the system. Positive is, again, something to enhance the system. So let me give you a really good example. And we'll start here. Again, we got the sun. Let me put the solar rays here so that you know what I'm talking about. And energy is coming in. So years ago, there was a big problem on our planet, and we're actually just recently gotten over it, and that's the ozone hole. There literally was a thinning of the ozone, and it was tantamount to the hole that we would typically see every summer season, I believed, in the southern hemisphere, but it would grow and expand as well. The question is, why were we getting this ozone hole or ozone thinning? And by the way, we're going to talk about the atmosphere soon, but ozone is a molecule comprised of 3 oxygen atoms together. Ozone is found in the stratosphere of the atmosphere over here, and ozone protects us from high energy ultraviolet rays coming from the sun. It's not 100%. If it was 100%, you wouldn't be getting your suntan and your sunburn because those are coming from ultraviolet rays. But without O3, ozone, we'd have a lot more cases of skin cancer and stuff like that. So ozone plays a really important role, frankly, in our health on the planet. Many years ago, though, there was a chemical in high use called CFC, or chlorofluorocarbon. Chlorofluorocarbon was used in various aerosol cans, and it was a big deal. It was used a lot by humanity for various purposes. And so humans' use of chlorofluorocarbon went up. And again, this was a handful of decades ago. Because the use of CFC went up, CFC concentration in the atmosphere also went up. Because CFCs actually break down ozone, and we didn't know this at the time, we not being me and you, but we being the people before us who came up with this nonsense, CFCs break down ozone. So the ozone levels in the atmosphere actually started to go down. And as the ozone levels went down, ozone's ability to block ultraviolet rays also went down, which means that UV levels at the surface went up, which means rates of skin cancer went up. And then finally, humans' use of CFCs had to go down. That's the negative feedback loop. And in this case, the negative became a positive. Now, by the way, this was amazing. This happened, I believe, in the 1970s or so. The world actually got together. They analyzed the destructive nature of CFCs. And as a collective human community, everybody decided to reduce or limit the use of chlorofluorocarbons. This was not an overnight success because chlorofluorocarbons last for like 50 years in the atmosphere before they break down. But now what we're seeing is a complete reduction and a reversal of the ozone thinning because the world community actually got together, recognized the problem, and started to reduce the use of chlorofluorocarbons. So again, this is a nice example of a negative feedback loop. And frankly, whatever we do when we talk about physical geography, if you can think in terms of feedback mechanisms, that's going to go a long way. Let me give you another one anecdotally, really quickly, because we're going to talk about this much more later on in the future. Let's say that there's global warming. What happens with global warming? Ice caps begin to melt. If you have less ice, then the surface albedo of the Earth changes. So albedo is albedo is meaning how much reflection or absorption does a surface have. Ice has high reflectivity or high albedo. So if you've got a lot of ice, then solar radiation will come in, it'll bounce off the ice, a lot of it will go back up out into space. But if you melt the ice, then we reduce the albedo on the Earth, which means more energy is going to get absorbed by the planet. So here's the feedback mechanism. Global warming occurs for whatever reason. We'll figure out why later. Ice begins to melt. Less ice means more energy into the system because the albedo has changed. More warmth means even more melting. More melting means even more warmth because more energy is absorbed. It's a feedback mechanism. This is a positive feedback mechanism or loop. But then over time, we have more water to absorb energy. This water also absorbs more carbon dioxide because water absorbs carbon dioxide. You remove CO2 from the atmosphere. CO2 is a greenhouse gas. So if you can remove it, then you'll have cooler temperatures in the atmosphere. Cooler temperatures will encourage more ice growth. That'll eventually alter the albedo the other way, and so on and so forth. So again, feedback mechanisms are a way for the natural system to maintain equilibrium. When we get in trouble on Earth, it's because we are messing with the equilibrium. We're infusing ourselves in the feedback process, and that creates problems, which makes sense. All right. So with all that said, what is physical geography? Geo is Earth, graphy is picture and writing, physical is physics. So we're going to examine Earth from place to place and over time. Physical geography is both a spatial and a physical science. And the ultimate goal of this class is to understand the four major Earth systems. And perhaps most important, at least for me, which means it'll be important for you, is what is the human or the anthropogenic role or influence in this entire process? It's a really important question. So with that in mind, we're going to have 6 major themes for the classes, for this class. Number 1, We're going to take a look at location, both absolute and relative. We're going to look at place characteristics, mountains and soils. We'll look at spatial patterns and distribution, i.e. vegetation, rainfall, earthquakes. We're going to look at the spatial interaction of stuff, vegetation to precipitation, El Nino to weather. We'll look at ever-changing Earth, how does weather change, volcanoes and ecosystems, and of course, we're going to look at human interactions and influence. Really important stuff. And I personally think this is one of the more important classes you'll take, that anybody will ever take. I just love it. Physical geography is wonderful. And if you take a look just at some of these pictures, you sort of go, okay, it is. Like, what is this? This is Aurora Borealis, the Northern Lights. This was taken in Iceland with an iPhone. What's causing this? Why is it this way? Here's another cool feature. This is a big waterfall, also in Iceland. Why is this there? What's it coming from? Why is Iceland even there to begin with? And here you see some outgassing of various fields in Iceland. But then what's sort of cool too in all of this conversation is this picture here. I'm eating an ice cream cone. But that's not the cool part. And I'll let you digest this for a second and you can think about this. What do you think that topping is on that ice cream cone? I mean, you could go to Dairy Queen and with a soft serve, you can get it dipped in chocolate and caramel and butterscotch. That's not what this is. What is it and why? Well, the answer is it's licorice. And you might be saying, well, is it good or did it suck? And it was actually really good. And I'm not a big licorice fan. But then the question is, why is this important in Iceland? Does it have something to do with physical geography? It might. That's a conversation that we're going to have. So everything you look at, think of it in terms of physical geography and the connection that physical geography makes with culture. And we're going to determine whether or not those are relationships that we can explore even further. And if we can, it becomes a lot of fun. So I'm sure you've taken a look at the course outline at this point. We're going to cover a lot of cool ground. We're not just looking at, places. That's old school geography. That's not what this class is. We do have map quizzes, which I'll talk about in just a second. But learning places is only important for us because if I say Iceland, I need you to know where it's located. Because where it's located says everything about why Iceland is the way it is. So we do map quizzes so that we know those things. We want to know where rivers are and mountains and things like that. It's a physical geography class. We're going to study weather and climate. We want to know what causes the seasons. We want to take a look at vegetation and see how vegetation is distributed around the planet. But we also want to look at geology. I want to know what created Iceland. I want to know what creates volcanoes and earthquakes and how that influences people and place. All of that is physical geography. So we actually do have quite a bit to cover, but it's a lot of fun. We have 16 weeks or so to do it, and I think we can.